Welcome to Physical Properties of Minerals Part 3. Already I have did Part 1 and Part 2. Hope you have followed that. Welcome to Part 3. So this includes our topics to be covered are isomorphism, polymorphism, enantiotropy, monotropy, paramorphism and pseudomorphism. Coming to isomorphism. So isomorphism means the minerals which have analogous or similar chemical composition and which crystallizes with similar structure, and hence they have similar crystal forms are said to be in isomorphism. So minerals which have the same chemical formula or same chemical composition, they will crystallize under similar structure and hence they have similar crystal forms are said to be in isomorphs. So popular examples we can say that, or best examples, plagioclase feldspars, garnet group, pyroxenes, amphiboles. And it's an important factor is the important factor in isomorphism is similar size relations of the different ions rather than the any chemical similarity. So the size relations, that is size of the cation or anion, in this is more important when compared to the chemical similarity. So in plagioclase feldspar there is a both replacement, the dual replacement of the ions, which can be best understood when the formulas of suppose albite, that is NaAlSi3O8, and anardite CaAl2Si2O8, it can be written in some form like instead of NaAlSi3O8, it can be written as NaAl Si2O8. So Si3 can be split up into two like Si and Si2. And similarly here CaAl2Si2O8, it can be split up as CaAl and again AlSi2O8. So like this, in this case, the NaSi of albite is replaced by CaAl of anardite, and this replacement it consists of calcium plus 2 ions for larger sodium ions and aluminium larger ions plus 3 ions for silica smaller ions. So like this the replacement takes place. And so this is in detail we can be expressed like this. These two minerals like the albite and anardite end members, with the help of a table we can understand very easily. So here the AB stands for albite and AN stands for anardite. The chemical compositions of the plagioclase feldspars, it is shown in the next slide, that is albite, oligoclase, andesine, labradorite, bitumenite and anardite. So AOALBA. So here we can see this is the mineral, plagioclase minerals like albite, oligoclase, andesine, labradorite, bitumenite and anardite. The composition it may vary like albite 100 and anardite 0. It may vary to albite 90 to anardite 10. So here the specific gravity is 2.61. Whereas in oligoclase, if we see albite 90, AN 10 and albite 70 and anardite 30. So these are in equilibrium, like so albite and anardite are in equilibrium. So here the specific gravity is 2.64. Whereas in the case of andesine, so AB 90 and anardite 10 and AB 70 and anardite 30. So here it has a specific gravity of 2.67. Similar the case of the labradorite, like AB 50 and AN 50 and AB 30 and AN 30. So this has specific gravity of 2.7, and bitumenite AB 30, AN 70 and AB means albite 10 and anardite 90. So the specific gravity of 2.72. Anardite AB 10, AB 90 and AB 0 and AB AN 100. So here the specific gravity is 2.75. So as shown in this table, the percentage of albite is gradually decreasing. You can see from albite to anardite, the percentage of albite is decreasing from here in the albite AB 100, whereas in labradorite AB 50, like that it is slowly decreasing. In anardite it is AB 10. So like that, and anardite is gradually increasing. If you see in the case of albite, anardite is 10, whereas in andesine it is AN 30, whereas in labradorite 70, bitumenite AN 90 and anardite AN 100. So like this, here the percentage of albite is gradually decreasing and anardite is increasing. And similarly, the physical property, especially the specific gravity, these are gradually increasing from albite to anardite. So it is the phenomena, we can say that where the two minerals have the same general internal structure. The structure will be the same and these are closely similar external morphology. So the external morphology is similar, it's not exactly the same, it is similar, and similar X-ray diffraction pattern. And the cause of phenomenon is that the exact mechanism or phenomena, it is due to the anions and cations of the same relative size and in the same numbers tend to crystallize in the same structure type. So here overall we can say that not only the plagioclase feldspats, even pyroxenes also, this phenomena like the anions and cations of the same relative size and also in the same number, they tend to crystallize in the same structure type. So very good example, another good examples we can say in the case of carbonate minerals like calcite, aragonite and magnesite and siderite. So calcite, aragonite, they have the same chemical composition CaCO3 and their slight physical properties may differ, and magnesite, siderite, similarly they have this is magnesite is MgCO3, siderite is FeCO3. So minerals in which the structure is exactly analogous and in which each and every ion in one mineral has the counterpart in identical environment in the other. This is known as isotope. Isotope means here the structure is exactly similar and analogous, and in this each and every ion in one mineral, it has the counterpart in the other environment. So this is known as isotypes. And isostructural means minerals in which the structure is basically overall the same, but not all the ions in one mineral have the counterpart, same as the case of isotopes, but it will not happen here. This is known as only the structure is same and not the mineral have counterparts. So this is known as isostructural. In isomorphism, the similarity in the size of the two ions, it is a very important factor rather than the overall chemical similarity. So here what is important, it is the size of the ions. Thus many calcium and magnesium compounds are not isomorphous. Why they are not isomorphous? Because they do not have the same size, although their chemical behavior is similar. So next is the polymorphism. What is polymorphism? Means poly means the name itself indicates that poly, number 1 or 2, more than 3, and the morphism means same morphology. Two or more minerals may have the same chemical composition but show different physical properties such as hardness, specific gravity, etc. And this phenomena of existence of a compound in more than one crystal form, and though they are in more than one crystal form, they possessing the different physical properties but identical chemical properties is known as a polymorphism. And two polymorphs contain the same number of atoms but with a different alignment. So that means even though they contain the same number of atoms, their alignment will be different. And when two minerals have the same chemical composition but show different physical property, this is known as a dimorphism. That means two minerals have the same and but they have the different physical properties. Similarly, when three minerals have the same chemical composition but show different physical properties, it is known as a trimorphism. And these are the excellent examples for dimorphism. That is carbon, it exhibits in two forms, that is in diamond and graphite. Here the diamond, it exhibits a cubic, and graphite, it is hexagonal. And similarly calcium carbonate, it exhibits in the form of it exists in the form of calcite and aragonite. Calcite is hexagonal, aragonite is orthorhombic, and Fe2, that is known as a pyrite and also marcasite. A pyrite, it has a cubic form and marcasite has a orthorhombic form. Here though the crystal structure is very important, diamond is very hard, and though it consists of same carbon, whereas in graphite it is not that strong, and due to the van der Waals bond, here diamond has a covalent bond. So the highest hardness of the diamond, it is due to this type of bonding. And in the example, we have said that just now I have explained, the first one, diamond, is the hardest mineral and it is a transparent, but graphite is very soft and it is opaque, but both the minerals have the same chemical composition. And in the second example, so if we say calcite and aragonite has a higher specific gravity than calcite. Then the other examples for trimorphism like a TiO2, so it exists like anatase, rutile and brucite. Anatase tetragonal, rutile tetragonal, whereas the brucite, it exists in orthorhombic crystal system. So this is another poly means more than 2 or 3. So like if you take SiO2, silica forms, it exists in quartz, tridymite, cristobalite and stishovite. All these are the polymorphic forms of silica. So quartz, it exists in hexagonal system, tridymite, it occurs in orthorhombic system, and cristobalite, it exists in cubic system, and stishovite, it exists in a tetragonal system. And stishovite is the highest pressure phases of a silica. And this is the aluminosilicate, Al2O3 SiO2 or Al2O SiO4. So both mean the same. So here it exists in like kyanite, andalusite and sillimanite. Kyanite, it has a triclinic crystal system, and andalusite is orthorhombic and sillimanite is orthorhombic. So polymorphism is an expression. It is due to the fact that here the crystal structure is not entirely dependent only on the chemical composition. Often there is more than one structure into which the same atoms may enter. So there are again two types of polymorphs, like enantiotropy polymorphs and monotropy polymorphs. So what is enantiotropy? Enantiotropy means in this case the polymorphs they change from one polymorph to another, and that change is reversible. Again, suppose if we take the excellent example, quartz, it exists in form of tridymite, the same silica, quartz, tridymite, and at a certain temperature it convert into cristobalite, but it can be happen reversible also. The same at that temperature, this is known as a transition temperature. Again, the cristobalite will become tridymite and tridymite. So this type of enantiomorph, this type of polymorphism is known as enantiotropy polymorphs, where the change from one polymorph to another is reversible. And monotropy. Monotropy means mono, the name itself indicates that it is a single transition. That means only one way. This is not reversible, it is irreversible. An irreversible polymorphic transformation is referred as monotropy. And excellent example, diamond to graphite. So diamond and graphite is a example for monotropy polymorph. And in this case, suppose if we take diamond, it may change to graphite, but graphite will not convert to diamond. The case with the marcasite and pyrite. Pyrite and marcasite is an example for monotropy. In this case, the marcasite may change to pyrite, but pyrite will not change to marcasite. So these are the very excellent examples for monotropy. Then next phenomena is known as a paramorphism. What is paramorphism? Paramorphs means, in paramorphs, the atomic rearrangement takes place without the chemical composition. So chemical composition will not alter, only just the readjust or rearrangement, atomic rearrangement takes place. Polymorphs, these are possible only in the case of polymorphous substance. So some type of polymorphs, they will become as a paramorphs. Suppose for example, if we take argentite, this is known as a Ag2S, it's a chemical composition. So this argentite, it crystallizes in cubic system or isometric system. So this is above 180 degrees centigrade, it is known as argentite. But the same argentite, if the crystals they fall below, that means the temperature is below 180 degrees, the same argentite, it become as an acanthite, where here the crystal system belongs to monoclinic system. So here at a certain temperature, that means above 180, the same argentite, it will behave as an argentite and in the form of cubic system, whereas below 180, the same argentite crystals, they become acanthite. So this acanthite is it belongs to monoclinic system. So here the acanthite, though the argentite has converted into acanthite, but acanthite, it will retain the cubic shape of the argentite. So because argentite is a cubic, and this acanthite will retain the cubic shape of argentite crystals. So in this case, the two minerals are referred to as the pseudomorphs of acanthite after argentite. Next is a pseudomorphism. Pseudomorphism is the assumption by a mineral of a crystal form other than to which it really belongs. So it is just assumption of a mineral of a crystal form other than to which it really belongs. For example, if you take the mineral pyrite, it alters to goethite. So even after the alteration of a new mineral like goethite, so this goethite, it retains the crystal form of the original pyrite. So here pyrite will alter to goethite, and even after the alteration to the goethite, so this goethite still it retains the crystal form of the mineral pyrite. In this case, the two minerals are referred as pseudomorphs of goethite after pyrite. So this is an excellent example. Next is the compounds that exhibit external shapes which are inconsistent with the internal arrangement of the ions. Overall, it is said to be pseudomorphs. That means they exhibit the external shapes which are not in arrangement with the internal arrangement. So that means the internal arrangement and the external will not coincide. So the this pseudomorphism, it may occur due to different properties or different factors like substitution. Some minerals may, some ions may substitute, and then incrustation. Some minerals may develop at the spaces, empty spaces like that. It is known as incrustation or infiltration. Some minerals may be infiltrated, and it may be also be due to alteration. So pseudomorphism may occur due to all these factors like substitution, incrustation, infiltration, alteration. And there are several types of pseudomorphs. Number one, we can say that pseudomorphs by investment or incrustation. So here what will happen in this investment or incrustation, because in this case a mineral or material, it is deposited on the crystal form of another mineral and it completely encloses it. That means it will cover the earlier one. So example, quartz and fluoride, these are said to be pseudomorph by incrustation or investment. And in the second case, pseudomorphs by alteration, the mineral garnet, it alters to chloride. So the chloride, it retains the crystal form of the original garnet. And these the two minerals are said to be as a pseudomorphs of chloride after garnet. So this is the example, like garnet alteration to chloride is an example of pseudomorphs by alteration. The other type, third type, it is pseudomorphs by infiltration. So a pseudomorph by infiltration that is formed, suppose if a cavity is formed and this cavity is occupied by a crystal, and it is again that cavity is refilled by deposition of a different mineral by the infiltration, suppose due to the magma process or due to the infiltration of a solution. So this may happen. So this is in this case the pseudomorph by infiltration is formed when a cavity it is occupied by a certain crystal, it is refilled by the deposition of a different mineral. Okay, so this is known as a pseudomorphs by infiltration. Next, the fourth type, it is known as a pseudomorphs by substitution or replacement. So here the replacement, it's a very slow process where here one molecule of the original material is removed in solution. There it is taken by the molecule of the replacing material. Suppose if it is quartz after calcite, and similarly quartz after fluorite. So like that it may happen due to, it's a very slow process like pseudomorph by substitution, or it's also known as a replacement. Either it can be substitution or it can be replacement. So excellent examples like quartz after calcite and quartz after fluorite. Thank you. Hope you have enjoyed all these phenomena. See you in the next video. Thank you.